Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss locating cardinal points. Let's begin. In the previous video lectures, we understand about cardinal points and cardinal planes in an geometrical optics and an idea of matrix representation of geometrical optics. So, with the help of matrix representation in geometrical optics, we can easily understand what should be the location of cardinal points in an geometrical system. So, let us start. Consider an optical system with optical axis x dash at the optical axis. Let two planes here this plane I, plane double I, that is the input plane, that is the output plane. The input plane has the refractive index mu I, output plane have the refractive index mu O, and inside that of input plane and output plane, the medium has the refractive index mu. Let F1 be the first focal point and F2 be the second focal point, P1 first principal point, N1 first nodal point. Here P2 second principal point, N2 second nodal point. The plane passed through that of principal point is known as the principal plane. That is the first principal plane. This one is the first principal plane. That one be the second principal plane. Second principal plane. The first incident ray is incident on input plane, at point A, then the ray emerges it is the emergent ray at point B parallel to that of optical axis. So the angle sustained to that of incident ray beta I, here the angle beta I, same angle beta I, and the height yi, that point be L, at that point T, that is the incident ray. At the emergent ray. Next, let another ray which is parallel to that of optical axis after refraction on that of plane the emergent ray towards the second focus. Here is the incident ray, that is the emergent ray. At point C, at point S, point D. So here the angle sustained beta I is equal to 0 and here the angle beta O, beta output, same as beta output, so that angle is same beta output. Here the height YO, Y output, same thing, the distance is same as this distance, so that is Y I. Let this distance means the distance from first means the input plane to the first focus is x1. By using the sign convention, if we measure the distance against the incident ray, then it will be treated as negative, x1 is negative. If it is with the same direction of incident ray, then it is taken as positive. Upper that of optical axis taken as positive, lower that of optical axis taken as negative. Same thing here. Here is the distance r1, that be positive, first focal length f1 which is negative. Same thing for that of output plane. Here is the distance x2 which is positive from focus to that of plane. Here r2 with a negative and focal length f2 is positive from focus to that plane. That is for ray 1. This one for ray 2. Now we locate the points like x1, f1, r1 and x2, f2, r2 for the cardinal points as for first focal point, second focal point, first principal point, second principal point and first nodal point and second nodal points in terms of system matrix. First one, location of focal points. To calculate focal points, here f1 and f2 with the two focus, f1 is the first focal point and f2 is the second focal point. Here the coordinate of point A is yi, beta I and coordinate of point B yo, beta O. Here the coordinate of that point A y I, beta I, that for input one, that one with the output one, the coordinate yo, beta O is the coordinate of point B. So we can represent it in the matrix way. The matrix representation as the output yo, beta O, that is the output matrix, is a system matrix. Let that system matrix be A, B, C, D are the components of that of system matrix. Then the input matrix yi, beta I, that is the matrix representation of geometrical optics. This is the input matrix, that be the output matrix. So the input matrix gives rise to the output matrix as the multiplication of system matrix. That one is the system matrix. So under matrix multiplication, if these two are multiplied, so we have y naught beta naught or y0 beta 0, yo beta O. What we read it, row to column. So it is written as A yi plus B beta I, then C yi plus D beta I. Now equating, the equations look like this: y naught is equal to A yi plus B beta I, equation number 1, and beta naught is equal to C yi plus D beta I, that equation number 2. Now our aim is to calculate the cardinal points in terms of the system matrix. First we calculate the focal points. To calculating that one, look here, in case of second ray, or if you treat the first ray, here the emergent ray is parallel to that of optical axis. That's why at that particular plane beta naught or beta output is equal to 0. Look here, since the emergent ray is parallel to optical axis, that is beta output is equal to 0. Therefore 0 is equal to Cyi plus dBi, or Cyi is equal to minus dBi, or Yi is equal to minus d by C beta I, or Yi divided by beta I is equal to minus d by C, minus d by C. Let it be the equation number 3. Okay, now look that figure here. From the right angle triangle F1 AL, from the right angle triangle, from right angled triangle F1 AL, this triangle F1 AL, so tan of beta I, tan of beta I, tan of this angle is equal to its perpendicular to base. So perpendicular is Yi to Yi, treat as positive, upper of that of optical axis. Then F1L, from input plane to the focus against that of incident ray, so the distance be negative, that is minus x1. So minus x1. Since we take the paraxial rays, the angle is very very small. As we take paraxial rays, tan of beta I is nearly equal to beta I. Therefore instead of tan beta I can write beta I is equal to minus Yi by x1, or x1 is equal to minus Yi by beta I. This negative sign is due to the sign convention as we prefer here. Now Yi beta I, the value of Yi beta I is equal to d by C. So the value is put here. So x1 is equal to minus of d by C. So minus minus plus, that is d by C. That one is the distance of the first focal point, that is the distance of first focal point, that is F1 from input axis, let I dash. Here is the input axis, let I dash. That one be the output axis, let O dash is the naming of that output axis. So x1, now x1 is found out in terms of the system matrix. X1 is equal to d by C. X1 is the distance of first focal point F1 from the input axis. Now from the triangle, look here, this big triangle F1 P1 T, from right angled triangle P1 F1T, if we take the tan of this angle, that is this side to that side, this side is equal to y naught, that length is equal to the focal length f1. So the tan of this angle from that triangle f1t, tan beta I is equal to y naught as positive sign for focal length, that is the minus f1. Again for paraxial rays, that is very similar to that of beta I is equal to minus y naught by f1. Here the value of y naught, I can write it like this. If f1 is there, so f1 is equal to minus of y naught by beta I, or f1 is equal to, in place of y naught, look that of expression, y naught is equal to a yi plus b beta I, that value is put here, minus a yi plus b beta I divided by beta I. Under solving that bracket term, so f2 is equal to minus a yi divided by beta I plus beta I cancel out plus b. Look here, yi by beta I, yi by beta I is equal to minus d by c. So the value is put here, or f2 is equal to minus a, that is d by c, plus b, or f2 is equal to minus plus ad by c minus b, or f2 is equal to ad minus bc divided by c. But we know that the determinant of system matrix as if the system matrix is a refraction matrix, is equal to mu input to mu output, refractive index of input to refractive index of output, means the system matrix as refraction matrix. So determinant A B C D determinant is equal to mu I divided by mu O. Now solving the determinant, so AD minus BC is equal to mu I divided by mu O. AD minus BC, instead of AD minus BC, therefore F2, in place of AD minus BC we substitute mu I divided by mu naught. So mu I divided by mu O into 1 by C, that is the value of, okay, that the, look here, that is a F1 not F2, that is F1, that is the F1 first focal length, F1, that is the first focal length F1 in terms of system matrix component 1 by C, mu y by mu o into 1 by C. Next we can calculate F2 for ray 2. For ray 2, look that figure, ray 2 beta I is equal to 0 as it is parallel to that of optical axis. Beta I is equal to 0. So the equation changes to, therefore equations will be y naught is equal to a yi, as beta is equal to 0, that term vanishes. Next beta naught is equal to c yi. Now dividing these two, here we have beta naught by y naught is equal to c yi divided by a yi, or beta naught by y naught is equal to c by a, or beta naught is equal to c by a into y naught. That value is needed. Again look our figure. Here that figure, let that point be M, D F2. This is the right angle triangle. So tan of beta 2, tan of beta naught is calculated here. Again taking the big right angle triangle, tan of beta naught is calculated. Now from this right angle triangle, from right angled triangle MDF2, so tan of this angle is equal to, here MD by MF2. So MD, look here, MD, the distance is the YO, MD. So putting these values, it is minus below that of optical axis minus y naught divided by its distance, that is x2, which is positive, x2. Just use the sign convention here. Now for paraxial rays, it will be same to that of angle beta naught or beta 0 is equal to minus y naught by x2. Therefore the value of beta naught, we can put here the value of beta naught, that is y naught, the value of beta naught is c by a into y naught. So the value of beta naught is put at c by a y naught is equal to minus y naught by x2, or C by A is equal to y naught cancel out 1 by x2, or x2 is equal to minus A by C. That negative sign is just for sign convention. Now x2 in terms of system matrix components, which is, this is the distance of second focal point F2 from output axis O dash. Again we calculate F2 in terms of system matrix. So calculating F2, we take the big right angle triangle here in that of figure. The right angle triangle P2 F2 S is considered. Tan of this angle is equal to this divided by that one is be the F2. Now taking that right angle triangle, from right angled triangle P2F2S, tan of beta naught is equal to the distance taken as negative as you take below that of optical axis, focal length it as positive F2. For paraxial rays, same as beta naught minus yi divided by F2. Now the value of beta naught is put here, that is C by A y naught is equal to minus, in place of yi we can put that expression y naught is equal to A yi. So yi is written as y naught by A here, y naught by A. So y naught divided by A F2, y naught cancel out. So C is equal to minus, again A cancelled out, 1 by F2. Therefore F2 in terms of system matrix minus 1 by C. This is the second focal point. So here we calculate the cardinal points as focal points. X1 as d by c, next f1 mu y by mu naught 1 by c. Taking the ray number 2, we have x2 and f2, this for focal points. Now second pair of cardinal points as principal planes and principal points. Second one, for principal points, as first principal point, second principal point, and the plane passes through that of principal points is named as principal planes. Look figure is important to calculating the locations of these cardinal points. Here this is the first principal point. So in place of f1p we can write that is f1l plus lp1. So f1l is the x1, lp1 that is the r1. I can use the sign convention here. Now for principal points, from figure, p1 f1 is equal to lp1 plus L F1. Now using the sign convention, P1 F1 that is minus F1 L P1 that is R1 L F1 minus X1, just use the sign convention, or R1 is equal to X1 minus F1. Now the value of X1 is put here, X1 and F1 the value is put. So R1 is equal to the value of X1, as we derive the value X1 d by C minus the value of F1, mu y divided by mu o into 1 by C. Here mu y divided by mu o into 1 by C. Now simplifying it, R1 is equal to d minus mu y mu o C as LCM, that is R1 in terms of system matrix. Next, R2 is calculated. Look that figure, this is the value of R1. Next, R2 is calculated. From that of figure, P2 F2 is equal to P2M plus MF2. Then using sign convention, we can solve R2 in terms of system matrix. Also, P2 F2 is equal to MP2 plus MF2, that is F2 is equal to minus R2 plus X2 using the sign convention. Next, R2 is equal to X2 minus F2. Now putting the value of X2 and F2, R2 is equal to value of X2 minus A by C minus A by C. Next, F2 minus 1 by C minus plus 1 by C. Therefore, R2 is equal to 1 by A by C. This is R2 in terms of components of system matrix. In this way, we locate the principal points. As we find out R1 and R2, R1 is the distance of principal point from that of input plane, and R2 is the distance of principal point from that of output plane. This is the first principal point, that is the second principal point. Now, third number, two conjugate nodal points, another cardinal points. How to locate nodal points? Number 3, location of nodal points. Nodal points, two nodal points, as first nodal point and second nodal point. Let look at that figure, that is the optical axis. First input plane, this is the input plane, not first, that is the input plane, that be the let output plane, that one is the incident ray, which is incident at point E, that is emerges like this, which is parallel to that of incident ray. This is the emergent ray, that that is the first nodal point n1, that is the second nodal point n2, the distance yi, angle sustained here beta I, angle sustained here let beta O, the distance at yo is the point let L, point M and K. Again this distance treat as T1, which is positive as a sign convention of that length. Then that distance from that point to that nodal point, that is T2, that is taken as negative. That angle also taken as negative in terms of sign convention. In this case, beta I and beta O are same. Here beta I is equal to beta O let beta. Therefore, the equations are changed like y naught, the pair of equations y naught a yi plus b into beta. In place of beta I substitute beta. Then for beta naught, that is beta is equal to c yi plus d beta. These are the two pair of equations. That equation number I, or equation number A and equation number B. From that of figure, from the right angle triangle L N1E, tan of this angle is equal to that by this. From right angle triangle, from right angled triangle L N1E, tan of this angle, that is negative, tan of beta I, this angle is sign convention use here, so negative angle, that is tan of minus theta, that is minus tan theta. So minus tan of beta I is equal to, that is yi positive divided by its length, that is T1 also positive. Again for paraxial rays, it is equal to beta I is equal to yi divided by T1. Now beta I is equal to beta. Since beta I is equal to beta, therefore minus beta is equal to y naught by T1. Next, put this value in case of equation number B. Therefore, equation B is written as, it is minus here beta is equal to c yi plus d beta, or beta minus d beta is equal to c yi, or taking beta as common, so 1 minus d is equal to c yi, or yi is equal to 1 minus d by c into beta. Again the value of beta is put here in place of yi, so yi here is the yi is equal to minus beta into T1, y is equal to minus beta into T1. Therefore minus beta into T1 is equal to 1 minus d by c into beta. So b cancel out, therefore t is equal to T1 is equal to, minus is multiplied here, so d minus 1 by c, d minus 1 by c, T1 that is the distance of first nodal point from the first input plane T1 in terms of the system matrix. That is this locates first nodal point N1. Next, the location of second nodal point N2, again taking the right angle triangle here N2MK from right angled triangle M N2K using angle sign convention, that is negative tan beta O is equal to minus YO divided by minus T2, that length negative, that length negative, below that of optical axis negative, against that of incident ray also negative, negative negative positive. For paraxial rays it is nearly equal to beta naught y naught by T2, that is minus y naught by T2, that is beta, y naught by T2 which is equal to minus beta is equal to y naught by T2, as beta I is equal to beta O is equal to beta. Next, y naught by T2 is equal to minus beta, or T2 is equal to minus y naught by beta, y naught by beta. So the value of y naught is put here minus 1 by beta, the value of y naught like AYI plus B beta. This is the value of YO or y naught. Now yi value and the value of yi is put, so T2 is equal to minus 1 by beta A, the value of yi 1 minus D by C beta plus D beta. This is the value of yi. One minus D by C into beta. Now solving it, we have T2 is equal to minus, taking beta as common and beta beta cancel out, inside that bracket we have A 1 minus D divided by C plus B, or T2 is equal to minus A, taking LCM 1 minus D plus BC divided by C. Look here, if we take the determinant of system matrix, it is equal to mu y by mu naught, as determinant A, B, C, D is equal to mu y divided by mu naught. Solving the determinant, it is AD minus BC is equal to mu y divided by mu naught. So instead of AD minus BC, AD minus BC, we can take it here. Solving that bracket term, it will be minus A plus AD minus BC divided by C. In place of AD minus BC, I can substitute mu y by mu naught. Therefore T2 is equal to mu y by mu O minus A divided by C. The second nodal point location of second nodal point in terms of system matrix. This locates second nodal point N2. Look that expression. If mu I is equal to mu naught, means the refractive index before that of input plane and after that of output plane be same. At that of case, here 1 minus A by C, that means T2 is equal to R2 as we treated in the first one, and T1 is equal to R1. So the principal point coincides with that nodal points. R1 with the location of principal point, T2, T1 is the location of nodal points. So T1 and R1 be equal. Again, the focus first focal F1 is equal to negative of F2, means the magnitude of first focal length is equal to the magnitude of second focal length, and the separation between R1 and R2 and separation between the nodal points T1 and T2 be same. These are the possible cases when the refractive index mu I is equal to mu naught. The special case. So with the help of this video lecture, we understand locating cardinal points for focal points that is the x1 with the distance of first focal point f1 from that of input plane. Next, the value of f1 taking ray 2, we get x2 and f2, x2 and f2. Next, for principal points r1, r2. Next, for nodal points we get T1 and T2. These are the cardinal points, the location of cardinal points in terms of system matrices, components of system matrices. So with this useful and informative notes, let me wind up this session. Thank you.